what role will AI and machine learning play in the 6G test and measurement platforms that your folks are busily working on even today?
Yeah, so a lot of AI starts with data. Having good data to be able to train the inference algorithms, that's really critical, right? So, the way that we look at it is that while we do incorporate AI into our products, and we're looking at different ways of doing that, we can speak to some of it. Part of that is, for example, just in terms of helping people optimize measurements. What we find nowadays is that a lot of our customers are just they're asked to do more and more every day, and so sometimes the test and measurement portion is the area that they're still not able to dive deeply enough in. So having test equipment that's a little bit smarter, if you say, hey, I'm trying to measure this, can I optimize for these types of things? Those are things that we definitely want to help our customers with. The other side of it really is just data management and generating that data. So what you want to have, for example, within the sort of the next release of the 3GPP is the use of AI and beam management for communication. So, well, how do you train those AI beam management algorithms? Well, you need lots of data. You need to be able to simulate good channel models. You need to be able to generate that, and then you need to be able to pull that data, potentially exclude outliers, things like that. And so, as a high quality data generation engine, that's, I think, one of the key roles that test and measurement is going to play, to be able to do some of the emulation around that and be able to create that data, and then also provide more open instrumentation so that customers may want to test their algorithms either through running something on an external GPU and then being able to pull that data in as quickly as possible into the test and measurement instrument. So adding kind of streaming capabilities for that data, or having a open platform. So potentially people want to look at more real-time applications. So an open FPGA type platform within the instrumentation is also kind of critical in those areas. And so that's on the test side, but Keysight also does a lot of design work, right? So we do a lot there. And what we're seeing there is that AI can also play a part in device modeling, right? So sometimes some of these devices have physics-based models or compact models or these behavioral models. And for behavioral models specifically, what we can do is potentially use things like artificial neural networks to model transistors, right? That's one of the areas that's very active in the research, and so we've done that in the past, and we continue to try to improve these device modeling capabilities so that designers can have access to these very complex design spaces where when you're designing an amplifier, you might want to look at things like different load impedances, different bias levels, and how do you create a small model that the compact model that has all of that data without necessarily having to have all this just large list of all the data that you needed to generate that.
Okay, sure. And you've perfectly led me into the next question I was going to ask you, which is to do with another topic we hear about is digital twins, to prototype transmitters, receivers, the whole network. And even as you were just talking about smaller models, digital twins requires a lot more detail to really adequately simulate such large systems. So how are we going to get to that level of simulation performance?
Yeah, so again, a lot more data generation required here. So some of the assumptions that we had, especially if we really want to capture the full behavior, especially for some of these nonlinear devices on the transmitter side, we need to have the VSWR or gamma dependencies in the model, right? That's one of the key things to kind of build up a system sort of digital twin, right? So if you want to build your transmitter, you can't just kind of say, well, I have a cascade of S parameters, everything looks good, call it a day. For sure, your power amplifier is going to be operating non-linearly, and people have kind of tried to do this in the past with potentially things like some TOI-based models, a third-order intercept, but if we take a look at a two-tone signal, those work really well when we're talking about narrowband signals, small peak-to-average power ratio signals that we used to use. Maybe I'm dating myself, but with WCDMA. But nowadays that we're in the world of, 5G, 6G, we're using these OFDM style signals, very high peak to average power ratios, nothing like a simple two-tone signal. So we need a much more complete understanding of the device's behavior under these realistic test conditions. So we need to have those models that do that. Conversely, again, kind of on the other side for the receiver side, the noise figure of an LNA depends directly on its source impedance, right? So we need to be able to have source impedance dependent noise parameter data or noise figure data, so that when we actually are, again, looking at, well, how is the noise figure of this LNA when we're actually putting it into this phased array and the impedances are changing, all of that needs to be kind of understood and well explained into kind of the system level digital twin. A lot of channel sounding still needs to be done for some of these different use cases that we're envisioning for 6G. So a lot of people are talking about, obviously the sub-terahertz, FR3, we need new channel models of that, better channel models, so that, we don't kind of make the same mistakes with the early 5G deployment. And then the other side is some of the integration that we want to do with these networks within drones or high altitude platform stations, or HAPS, as you might have heard. So this is kind of like a hot air balloon base station that's floating up there, reflective intelligence services. So we need to have a lot more data of exactly how all of these behave, so that we can actually build up a full network and emulate that.